Welcome to this lesson on medical ultrasound physics. Ultrasound is a fascinating application of physics in medicine. Instead of using visible light or X-rays to look inside the body, ultrasound uses high-frequency sound waves. The key idea is simple: we send sound waves into the body, they interact with different tissues, and some of the waves are reflected back to the transducer. By analyzing these echoes, the ultrasound machine can construct an image of structures inside the body. In this lesson, we will follow 4 important stages: generation, propagation, optimization, and interpretation. Let's begin by understanding how ultrasound is produced. One of the most important decisions in ultrasound imaging is the choice of frequency. Higher frequency ultrasound gives us better resolution. In other words, it allows the machine to distinguish between structures that are very close together. However, there is a disadvantage. High-frequency ultrasound is absorbed more strongly by tissue, so it cannot penetrate very deeply. Lower-frequency ultrasound behaves differently. It can travel deeper into the body because it experiences less attenuation, but the resulting image has lower resolution. So there is an important diagnostic trade-off. High frequency gives better resolution but less penetration. Low frequency gives greater penetration but lower resolution. The appropriate frequency therefore depends on what structure we want to examine.
Now we come to the mechanism that makes ultrasound possible, the piezoelectric effect. Inside the ultrasound transducer is a piezoelectric crystal. When an alternating electrical voltage is applied to this crystal, the crystal changes shape rapidly. These mechanical vibrations produce ultrasound waves. The process can also work in reverse. When an ultrasound echo reaches the crystal, it causes the crystal to deform. This deformation produces an electrical signal. So the same crystal can perform 2 jobs. First, it converts electrical energy into mechanical vibrations to produce ultrasound. Then it converts returning mechanical vibrations back into electrical signals to detect the echoes. This conversion between electrical and mechanical energy is the heart of the ultrasound transducer. Let's look inside a typical ultrasound probe. At the heart of the probe is the piezoelectric crystal. This is the component responsible for converting electrical energy into mechanical vibrations and receiving returning echoes. The crystal is connected to the electronics through the connector and cable. Behind the crystal is a damping material. Its purpose is to absorb backward traveling vibrations and help control the duration of the ultrasound pulse. At the front is the acoustic window. This allows the ultrasound waves to leave the probe and enter the patient's body. Each component therefore has a specific role in producing and detecting a useful ultrasound signal. Once ultrasound enters the body, it doesn't simply travel in a straight line without interacting with anything. Whenever the ultrasound wave reaches a boundary between 2 different materials, several things can happen. Part of the wave can be reflected back towards the transducer. Another part can continue into the second medium, but its direction may change. This is called refraction. The important point for medical imaging is reflection. Different tissues have different physical properties. Therefore, when ultrasound encounters a boundary between tissues, part of the sound energy may return as an echo. The machine detects these echoes and uses them to determine where boundaries between tissues are located. To understand why ultrasound is reflected at tissue boundaries, we need the concept of acoustic impedance. Acoustic impedance is represented by the symbol Z. It is given by the equation Z equals rho C. Here, rho is the density of the medium, and c is the speed of sound in that medium. Therefore, acoustic impedance depends on 2 things: the density of the tissue and the speed of sound through it. Different tissues have different acoustic impedances. When an ultrasound wave travels from one tissue to another with a different acoustic impedance, part of the wave is reflected. The greater the difference in acoustic impedance, the stronger the reflection can be. We can quantify the amount of ultrasound reflected at a boundary using the intensity reflection fraction. The equation shown here is IR divided by I equals Z2 minus Z squared divided by Z2 plus Z squared. Here, I is the incident intensity and IR is the reflected intensity. The equation shows something very important. If the acoustic impedances on the two sides of the boundary are almost equal, the difference between them is small, so very little ultrasound is reflected. But if the acoustic impedances are very different, the reflected fraction becomes much larger. This is why acoustic impedance differences are fundamental to ultrasound imaging. Let's apply the idea of acoustic impedance to some important tissue boundaries. At a soft tissue boundary, the acoustic impedances are relatively similar. Therefore, only a small fraction of the ultrasound is reflected. At a soft tissue bone boundary, the difference in acoustic impedance is much greater. Consequently, a much larger fraction of the ultrasound is reflected. The most extreme case shown here is an air-skin boundary. The difference in acoustic impedance is enormous, so almost all of the ultrasound is reflected. This explains an important practical feature of ultrasound scanning. Air is a major obstacle to ultrasound transmission. This brings us to the reason ultrasound gel is used. If there is air between the transducer and the patient's skin, there is a very large acoustic impedance mismatch. Most of the ultrasound energy would be reflected at the air-skin boundary, meaning very little ultrasound would enter the body. The solution is to use coupling gel. The gel removes the air gap between the transducer and the skin and provides a much better acoustic connection. As a result, much more of the ultrasound energy can enter the body and return to the transducer. So the gel isn't simply used to make the probe move smoothly over the skin. Its important physics function is acoustic coupling. As ultrasound travels deeper into the body, its intensity decreases. This reduction in intensity is called attenuation. The slide shows the relationship. I equals IE to the power minus alpha x. Here, I is the initial intensity, alpha represents the attenuation coefficient, and x is the distance traveled through the tissue. The equation tells us that ultrasound intensity decreases exponentially with distance. Attenuation occurs because ultrasound energy is absorbed and scattered as it travels through tissue. This creates another important limitation for imaging. Echoes returning from deeper structures are weaker than echoes from shallow structures. The ultrasound machine therefore needs to compensate for this reduction in signal strength. Now let's see how the returning echoes can be interpreted. This is called an A-scan or amplitude scan. The ultrasound transducer sends a pulse into the body. When the pulse encounters boundaries between different tissues, some of the energy is reflected back. The machine records these returning echoes as peaks on a graph. The horizontal axis represents time, while the vertical axis represents the amplitude of the detected signal. The position of a peak tells us how long the ultrasound took to travel to a boundary and return. The size of the peak gives information about the strength of the reflection. So from an A-scan, we can obtain information about both the location and the strength of tissue boundaries. To determine the depth of a structure, we need to consider the time taken by the ultrasound pulse to travel to the boundary and return. This is a round trip. If the measured time is delta t, the ultrasound has traveled twice the depth. Therefore, the depth is given by d equals c delta t divided by 2. The factor of 2 is extremely important. Why? because the measured time includes both the journey from the transducer to the boundary and the return journey from the boundary back to the transducer. The machine uses the known speed of sound in tissue together with the measured time delay to calculate the depth of the reflecting boundary. An A-scan gives us information along a single line. But for medical imaging, we usually want a two-dimensional picture. This is where the B-scan, or brightness scan, becomes useful. The ultrasound probe sends pulses into the body at different positions or directions. The machine determines the depth of each reflecting boundary and uses the strength of the echoes to determine the brightness of the displayed points. Weak echoes produce relatively low brightness, while stronger echoes produce brighter points. By combining many individual scans, the machine constructs a two-dimensional image of the internal structure. So the B-scan converts information about individual echoes into a visual image. Let's compare the two scanning methods. An A-scan produces a one-dimensional trace of echo amplitude against time or depth. Its major strength is that it provides precise information about the position and depth of reflecting boundaries. A B-scan, on the other hand, produces a two-dimensional grayscale image. Instead of simply displaying peaks, it represents echo information as brightness at different positions. Therefore, A-scans are particularly useful when precise depth measurements are required, while B-scans are more useful for visualizing the shape, size, and boundaries of internal structures. In modern diagnostic ultrasound, the B-scan principle is fundamental to producing the familiar ultrasound images used clinically. Let's finish by bringing together the key physics ideas. There are 4 core equations to remember. First, the relationship between wave speed, frequency, and wavelength. V equals F lambda. Second, acoustic impedance. Z equals rho C. Third, the intensity reflection fraction. IR divided by I equals Z2 minus Z squared divided by Z2 plus Z squared. And finally, the A-scan depth equation. D equals C delta T divided by 2. There are also 3 major principles to remember. First, the piezoelectric effect allows electrical energy to be converted into ultrasound, and returning ultrasound to be converted back into electrical signals. Second, impedance matching is important because large differences in acoustic impedance produce strong reflections. And third, attenuation causes ultrasound intensity to decrease as it travels deeper into tissue. Finally, remember the distinction between the two scans. A scan, individual spikes represent depth and echo amplitude. B-scan, individual bright points are combined to produce a two-dimensional image. These ideas form the essential physics framework behind medical ultrasound.